Welcome, class. So, throughout this course, we've been working really hard to build up our foundation in business mathematics. We've gotten pretty comfortable with the tools of arithmetic and algebra, right? And those are fantastic for analyzing a static snapshot of a business. A balance sheet, a quarterly report. They give us a clear picture of a single moment in time. But let's be honest, the world of business, of strategy, of real growth, it's not a static picture. It's a motion picture. It's defined by constant dynamic change. So today, we're going to level up our analysis. We're moving from the math of fixed states to the mathematics of change itself. We are going to dive into the calculus of business strategy. Now, before we get lost in all the symbols and formulas of calculus, let's ground ourselves in a real-world problem, something you'll almost certainly face in your careers. I want you to imagine you're a product manager a few years down the line. Your analytics team comes to you with some really exciting data. Your new app, it's taking off. Specifically, it's being adopted at a rate of 5% of the untapped market every single day. Now that's a rate of change. That's a velocity. But your CEO, the board of directors, they don't think in terms of daily rates. They're going to ask, that's great, but what does that mean for our total market share at the end of Q2? So how do you get from that daily rate of change to a total accumulated value over a whole 6 months? Well, that translation, that is exactly what integral calculus is for.
The mathematical tool that we need for this job is called integration. And we're going to start by looking at a specific kind of integration that models one of the most powerful forces in business and, frankly, in all of nature, continuous proportional growth. Just think about it for a second. The more money you have in an account with compounding interest, the more interest it earns. The more people that join a social media platform, the more likely their friends are to join too. It's a self-reinforcing loop. Well, this exact phenomenon is modeled by what we call the exponential integral.
And here it is, the formula in all its elegant simplicity. Now, don't let how short it is fool you. This is powerful. The integral of e to the power of x is, well, it's just e to the power of x plus a constant. This function is totally unique. Its rate of growth at any given moment is equal to its size at that same moment. So let's break this down. That long S-looking symbol, that's our integral sign. I want you to think of it as meaning the sum of. And what are we summing up? In our product adoption problem, we're summing up every tiny little sliver of market share we gain. Not just every day, but every hour, every minute, every single instant. We're summing up an infinite number of these tiny changes over our 6-month period. And the function we're summing, e to the x, is the perfect mathematical model for that continuous compounding growth. So what exactly is this number e, also known as Euler's number? Honestly, it's one of the most important numbers in all of mathematics. For our class, I want you to think of e as the natural speed limit for growth. It represents the absolute maximum result you can get from any process that compounds continuously. Let me give you a classic example. Let's say you invest $1 at 100% annual interest rate. After a year, you've got $2. Simple enough. But what if you compound that interest twice a year? You'd actually have a little more. What about quarterly? Even more. Well, if you could compound that interest at every single instant, continuously, you wouldn't end up with infinite money. You'd actually approach a very specific limit. And that limit is E. It's the fundamental constant for any system, whether it's money or a population of cells, where the growth at any moment is directly proportional to its size at that same moment.
So its numerical value is about 2.718. But memorizing the digits is way less important than understanding what it represents. Its real power, especially in business strategy, isn't in the number itself, but in its role as the mathematical foundation for any system that's showing that kind of unrestrained compounding momentum. So from now on, when you see E pop up in a financial model or a projection, your brain should immediately think, okay, we're looking at the purest form of compounding growth right here.
Okay, now I really need your full attention here because I want to talk about what is, from a practical business perspective, the most critical part of this equation, the plus c. That's the constant of integration. And let me be perfectly clear, after years of teaching this course, I can tell you that forgetting to include plus c is the single most common and most serious mistake students make when they try to apply calculus to real business problems. Why? Because the integral itself, the integral e dx part, it only gives you the general shape of the growth curve. Think of it like a blueprint. But the plus c, that's what anchors that blueprint to a specific starting point in the real world. It's your initial investment. It's how many users you had on day one. Without c, you have an abstract idea. With c, you have a concrete, usable model.
I want this to be a major takeaway for you today. Without that constant c, your model is not just mathematically incomplete, it's strategically useless.
A growth curve that doesn't have a starting point is just a shape floating around in space. It's completely unmoored from reality. Defining C is how you tell your model where the story begins. Forgetting it is a fundamental error that will make any prediction or analysis you do completely invalid. Please do not make that mistake.
All right, fantastic. So we've laid out the theoretical groundwork. Now let's move from the abstract world of formulas to the applied world of business. We're going to see exactly how this exponential integral model translates directly into real dollars and cents, shaping investment decisions that can build massive amounts of wealth, all based on understanding this one core principle.
So, over here on the left, you see the annual compounding model. You probably remember this from your intro to finance classes. The interest gets calculated and added in discrete chunks once a year. It gives you a series of snapshots. It's a useful approximation for sure, but it's still just an approximation. Now, on the right, we see what's actually closer to reality. In the real world, value doesn't just appear once a year. It accrues continuously, moment to moment. And that's what our integral model captures so perfectly. It doesn't give us snapshots. It gives us a continuous film, a dynamic movie of how an investment actually grows over time.
This table really brings the financial impact to life. Let's walk through the numbers. We start with a $10,000 investment. After 1 year, the difference between the two models is just $12.71. Now, it would be really easy for a rookie analyst to look at that and say, who cares? It's negligible. But that's short-term thinking. The true power of continuous compounding reveals itself over the long haul. Look at year 5. That difference is now over $77. By year 10, it's almost $200. Now, and this is the part that really matters for you as future financial managers, I want you to scale this up in your head. What if you're not managing $10,000, but $10 billion for a major pension fund? That seemingly tiny mathematical difference now represents millions and millions of dollars in real value. This is the heart of long-term strategic finance, and it is built entirely on the principle of continuous compounding. This leads us to a really important question about the limits of the exponential model. It's incredibly powerful, but its main assumption is that growth is unrestrained. So what happens in all those other scenarios, the ones that are actually more common, where growth is constrained? What happens when we run into one of the most fundamental laws of economics, the law of diminishing returns? Think about your marketing budget. Does that second $1 million you spend on ads really bring in the same number of new customers as the first million? Of course not. In almost every real-world case, the answer is no. So for that, we need a different model.
For those situations, we need a completely different kind of mathematical engine. We need a tool that's designed specifically to model growth that starts out fast, but then begins to level off, to taper off as it gets closer to some kind of limit. And trust me, this pattern is just as common, if not more so, in the life cycle of any business, any product, or any market. And here it is. This is the logarithmic integral, our mathematical tool for modeling diminishing returns. Just look at the function we're integrating, 1 divided by x. This simple little function perfectly captures the whole principle. Let's say x is your input, your ad budget in dollars. When x is small, when you're spending your first few dollars, the value of 1 over x is huge. The impact is massive. But as x gets bigger and bigger, as you're spending your millions dollar, the value of 1 over x gets progressively smaller, getting closer and closer to 0. The marginal impact of each new dollar you spend diminishes.
And once you learn to recognize this pattern, I promise you, you will start to see it absolutely everywhere in the business world. Take asset depreciation. A brand new company car loses most of its value in the first year. Or market saturation. A new product's growth is super fast at first, but it has to slow down as it gets closer to reaching everyone in the market. Or the economic idea of marginal utility. That 10th slice of pizza just isn't as satisfying as the first one, right? Even training your employees. The productivity jump you get from the 10th week of training is almost never as big as the jump you got from the very first week. All of these very different situations are at their mathematical core, logarithmic functions. Okay, so let's put this all together. The goal here isn't for you to just memorize a bunch of formulas. It's for you to really internalize these concepts as mental models that you can use to analyze business dynamics. We can now distill everything we've talked about into 2 powerful, distinct tools that you can add to your strategic decision-making framework. So you now officially have 2 distinct tools in your strategic toolkit. You have the exponential model. That's what you pull out when you're looking at momentum, things like early-stage growth, viral marketing, compound interest. And then you have the logarithmic model. That's for analyzing maturity, things like market saturation, the life cycle of your assets, and the efficiency of spending more money on something.
Knowing which model to apply to which business situation, that is the hallmark of a truly sophisticated business analyst.
And this right here might be the single most important thing you take away from our entire discussion today. Your value as a future business leader will not be your ability to just punch numbers into a calculator. We have software for that. The math we're studying is a tool. It's a powerful lens that helps us see complex situations more clearly and illuminates our strategic options. Your real job, your higher purpose, is to interpret the story that the numbers are telling you, and then to use that story to make smarter, more informed strategic choices.
So I'll leave you with this final thought to chew on. Every single business problem, every opportunity, every threat you'll ever face, it has a rate of change at its core. The rate of technological adoption, the rate of shifting consumer tastes, the rate of inflation. Your challenge, and really your opportunity, is to identify those rates of change and to understand their underlying shape. And now you have the tools to model them and just maybe to predict what's coming next.